Greetings everyone, and thank you for joining this presentation. My name is Ioannis Kafetzis, and I'm going to present to you our work regarding a novel framework for accelerating chaos-based grayscale image encryption via parallel computing. First of all, what is chaos and how does it connect to pseudo-randomness? Chaotic systems are dynamical systems that exhibit extreme sensitivity to initial conditions, meaning that a very small change to initial conditions drives the system into a completely different trajectory. And there are, of course, both continuous time chaotic systems or discrete time, which we usually call chaotic maps. Both of them, but especially chaotic maps, have been also used as a source of pseudo-randomness. This exact sensitivity to initial conditions, the lack of periodicity, makes those systems behave like a cheap source of entropy, and cheap in the sense of computational efficiency. And this way they form, and it has been studied a lot, how we can use those systems as a basis for defining pseudo-random bit generators. That is, taking the values of a system or a map and converting them to random or pseudo-random sequences of zeros and ones. And having those random bit generators, a lot of chaos-based image encryption methods have been developed. And although each one of them is unique and provides its own merits, there is usually a standard approach to how those methods are defined, which is first, using the values of the chaotic map, the pixels in the image are shuffled, and this helps with breaking local correlation. And then, using the values of the pseudo-random bit generator and the XOR operation, the value of each of the pixel changes, resulting into something that usually looks like noise. And this process is invertible, but can only be inverted if the exact initial conditions used in the encryption are known. Although these methods are very commonly used and studied, they usually have issues, and mostly regarding their complexity and how heavily it depends on image size. That is, the larger the image to be encrypted, the more time is required for it to be encrypted. And this is relevant in many cases, for example in high definition images where the resolution is very high, or X-rays and medical image data in general. And to demonstrate this, and to also show how our method can be used, we consider two published chaos-based methods for image encryption, and we actually consider their official implementation. And as test data, we use more than 1,100 grayscale chest X-ray images that are also publicly available. And without further ado, let's see how the method does. On the y-axis we see the mean time to encrypt one image, and the mean based on the test images discussed before, and the x-axis is the image size, and actually it's one side of the image. So the first one is 64 by 64, second 128 by 128, and so on and so forth. And we can see exactly what we discussed, that as the image grows larger, so does the encryption time, and it increases exponentially. And this is for the first of the two methods, and we can see that it starts with very low values. If we check the distribution of the encryption times for all of the images, with 0.025 seconds, goes up to 0.08 seconds, but then as images grow larger, we have 0.3 seconds, 1.3, more than 5, almost 6 seconds, going up to a huge 24 seconds for a 2048 by 2048 image. If we consider the second method, we see very similar results, so it's not method bound. And we have the encryption time for 64 by 64 images being 0.025 seconds, again close to 0.08 for 128 by 128. We see that for 256 by 256, well, around 0.3 again, so we can see that there are similar results. 512 by 512 is almost 1.3, again almost 5 seconds for 1024 by 1024, going up to 24 seconds for 2048 by 2048. And the main takeaway for us is that for very, very small images, the encryption times are small. And this is what we want to actually use. So what we do is we simply, instead of taking the entire image and pass it through the encryption algorithm, we first split it into smaller parts. And those parts, first of all, take less time to be encrypted, and they can also be encrypted in parallel. And these are the two major points where we get time benefit. And the question is, how do we split it? Some methods in the literature actually considered splitting the image into boxes. We thought of splitting by rows. So in this case, let's say we want to split the image into 3 different parts by rows. So we take the first, 4th, 7th and 11th row, and this forms one part. And similarly will be with the 2nd and 3rd rows and the subsequent ones. And then each one of those rows we can also split by columns. Let's say we take again 1 every 3, and this will be the results for how it gets split. And this split is unique and it's standard. And the resulting images are much smaller than the original one. So we encrypt the smaller images resulting from this method, and then go back to reconstruct the image following exactly the steps of the decomposition. And this is also how the decryption is achieved. So to decrypt, we again get the exact same split, decrypt each one of the pieces that was uniquely encrypted before, and reconstruct the original image. And let's see how it does. In this figure, again, y-axis is mean encryption time, and x-axis is the size of an image, or the side of an image, and the light blue line is the original, and darker blue is our method. And we can see that as image sizes grow larger, we get a huge benefit, and similar results also come for the second method. But let's dive a bit deeper. For 64 by 64 images, for the first of the two methods, we see that without parallelism, we get smaller encryption times. Of course, both encryption times are small, but we see that for very, very small images, parallelism actually causes more overhead, so more computational overhead. When it comes to 128 by 128, we see that we have similar times. So again, parallelism doesn't provide any benefit, but things change as image size begins to grow larger. Where for 256 by 256 images, we have the original method with 0.3 seconds, at least as a mean, and a bit more than 0.1 second when we use parallelism. When we go for 512 by 512, we see that the difference becomes much larger, seeing that again the encryption time for the method when we use parallel is about a bit above 0.1 compared to the 1.25 seconds for the original one. 1024 by 1024, again the difference becomes even bigger, where the almost 6 seconds for the original method becomes less than half a second for our method. And finally, for the largest of them all, we see that the almost 25 seconds required from the original method are merely a 1.5 seconds for our method. And we compare the results with the second method as well, and we can see similar results. So for 64 by 64 and 128 by 128, we don't see that much benefit from using parallelism. But as image sizes grow larger, we see that parallelism starts to make a difference again, where the 0.4 seconds becomes 0.05. 1.5 seconds for 512 by 512 become merely 0.13 seconds. And same for 1024 by 1024, where 6 seconds stay around 0.5 to 0.6 for parallelism. And for the largest of them all, where we were almost 24 seconds with the original method, we have a mere of 2 seconds with the proposed one. And again, these results get achieved without having any changes to the original method. We just used the original encryption method more times on smaller images. And the question that comes to mind is, how many parallel processes should we run? And this is another thing that we investigated. Again, the y-axis is the mean encryption time for the two methods. And on the x-axis we see the number of workers, that is the number of parallel processes. And one might think that the more parallel processes we use, the faster the total encryption. But this is not actually true. We see that around 8 processes, at least for our setup, was the optimal number, and after that the overhead of managing those processes actually started to increase the cost in time for the method. To conclude, we introduced a method for parallelizing image encryption that works out of the box with existing methods, and it can be used with any other developed method without any additional overhead in the design. So the methods to be used that can be combined just require an image and the key as an input, and if they provide the encrypted image, they are compatible with our method. We saw that this method significantly reduces execution time, and it can also increase key space. And to see this, consider that we split the original image into smaller parts and encrypted each one of them. So for each one of those parts we can now choose a different encryption key, and this by default increases the key space, although optional, so we can have a method that is even more resistant to brute force attacks. How we plan to extend this work is we want to implement more splitting methods instead of only rows and columns. We also want to investigate the relationship between number of splits, so how many pieces we split the image, and the number of processes that we use, and also evaluate its implementation on low power devices and make the method publicly available. With that, I would like to thank you for your attention, and if there are any questions, feel free to reach out in the chat or via email. Thank you very much.